Okay, final question, question 7. We have 3 points, A, B, C, lying on the line of greatest slope, and the plane is inclined at an angle of 30 degrees to the horizontal. Okay, AB is equal to 1, BC is equal to 1, right, as shown in the diagram. We have a particle of mass, 0.2 kilograms. It's released from rest at A and slides down the plane. So from A to B, it's smooth. That's very important. In other words, there's no friction. And then the part from B to C is rough, and there's a coefficient of friction of mu and between the plane and the particle. So they give us the fact that this coefficient of friction is equal to 1/2 square root 3, and they want us to find the speed of the particle at C. So we're going to have to do this in 2 parts because there's different frictions acting on the object at different stages. So we'll first consider the first stage from A to B where there's no friction, and then we'll consider the stage from B to C. So what we need to do is find the speed of the particle when it reaches B, because its final speed at B will be its initial velocity for the second half of the journey. So let's take particle A, and what we want to do is consider where it's starting and stopping. So it's going to stop at B, and what we can do is we can draw a perpendicular line to the horizontal over here, and because they're parallel lines, this will also be 30 degrees. The next thing we want to do is we want to draw in our forces. So this particle was released from rest, so there's no force acting on the object, pushing it down the hill. So the only thing acting on the object is its weight, okay? And that will be 2 newtons. Now, this particle is not acting in the direction of motion. So if we want to draw the direction of motion in, the direction of motion is down the hill in that direction. So the weight force is not perpendicular or parallel. So what we need to do is we need to split it, resolve it into its 2 separate components. So the 2 components will be the weight pulling the object down the hill, and then this vertical component as well. So with a bit of geometry, we can work out this is also 30 degrees. So the only force acting in the direction of motion of this particle is the weight force component acting down the line of greatest slope. So that will be this force over here. Okay, so using Newton's second law, force is equal to mass times acceleration. The net force, well, the only force we have, is acting in the direction of motion. That is the opposite side to the 30 degrees, so it's going to be sine. So we'll have 2 sine 30 degrees equals mass times acceleration. The mass is 0.2, and the acceleration is what we're trying to calculate. So we should know that sine of 30 is 1/2, and if you multiply that by 2, you get 1. So 0.1 divided by 0.2, we'll get an acceleration of 5 meters per second squared. Okay, and we can just verify that answer. If we think about the object going downhill, logically we can work out it should be accelerating because it's going down the hill. Right, now that we have the acceleration, we are able to calculate its speed when it gets to point B. So let's consider what information we have. We know the initial velocity is 0. We know that the distance the particle travels is 1 meter. We've just calculated the acceleration as 5 meters per second squared, and we are after the final velocity. So we'll use this formula, v squared equals u squared plus 2s. And we have an initial velocity of 0, acceleration of 5, displacement of 1. Okay, and so we're going to get v squared equal to 10 and v equal to square root 10. We know it's positive square root 10 because the object is traveling in the direction of motion. So now that we have the speed at particle B, we need to think about what's going on. So let's just draw that particle B is now, there's the particle at B, it's at its new location, and let's now reconsider the forces acting on the object. So once again, we have the weight component, and we have friction, okay, because there's now a coefficient of friction. Friction is always acting against the direction of motion. So here we have friction, and in order to calculate friction, we need to know what the normal contact force is. And the normal contact force is the force that is perpendicular to the surface. So there's the normal contact force. Right, the next step is we just need to split the weight component once again up into two separate components. We have the weight component acting down the line of greatest slope, and we also have the weight component acting perpendicular to the line of greatest slope. Right, the first thing we'll do is we'll calculate the normal contact force. Now the normal contact force acts perpendicular to the direction of motion, and anything perpendicular to the direction of motion has no acceleration. So the forces in the perpendicular direction, so that are acting in this direction, they must be equal to each other or in equilibrium. So we can say that R, the normal contact force, must be equal to, and it's equal to the perpendicular component of the weight force. Okay, and that is the adjacent side from 30 degrees, and that's going to give me 2 cos 30. Right, now that I know the normal contact force, I can calculate the friction force. So friction is just coefficient of friction times the normal contact force. And they give us the coefficient of friction as 1/2 square root 3. Okay, and that's multiplied by 2 cos 30. So what is 2 cos 30? Well, it's 2, and cos 30 is square root 3 over 2. It's one of your exact values that you should know. So we're going to have a lot of cancelling happening, which is obviously very nice. So we're going to get this 2 cancelling out, and we can see we're going to have square root 3 times square root 3, which will create 3, and we'll have 3 over 2, which is the same as 1.5 newtons. So we have calculated now friction force. So if we return to our diagram, you can see we have the friction force now. It is 1.5 newtons. And we already worked out from the first part that this force acting down the hill, this is 2 sine 30. Okay, sine of 30 is 1/2, so 2 times sine 30 is equal to 1. Right, again, using Newton's second law, force equals mass times acceleration, we're going to consider the net force. So you can see that the friction force is greater than the weight component, so we can consider that we're going to get a deceleration. So we have 1 Newton acting in the direction of motion down the hill, and we have 1.5 newtons acting in the opposite direction. The mass is unchanged at 0.2, and the acceleration is what we're trying to calculate. So we're going to end up with minus 1/2 equal to 0.2a, and solving for a, we will get minus 2.5 meters per second. Okay, so the object is decelerating towards C. Almost done. Let's consider the information we have now. Okay, we have the initial velocity. Right? The initial velocity for the second part of the journey is the same as the final velocity from the first phase. That's what the object was traveling at when it got to the friction part. So this will be square root 10. We have the acceleration, which we just worked out as minus 2.5 meters per second squared, and we know the object is going to move 1 meter. So again, using the same equation, v squared is what we're trying to calculate. U squared is going to be square root 10 squared, which is just going to be 10 plus 2. The acceleration is minus 2.5, and the displacement is 1. That's going to give me v squared equal to 10 minus 5, which is just 5. And so v is equal to the square root of 5. What we need to do now is we need to convert this to a number. So we're going to get, if you put that in your calculator, get 2.23606. And now we just need to round to 3 significant figures. So 2.24 meters per second. So that is the velocity of the object after it gets to C. Okay, now they say given instead that the particle comes to rest at C, they want us to find the exact value of the coefficient of friction mu. So what we're going to do is we're going to take our working here and we're just going to work backwards, okay? So let's first consider we have what type of acceleration the object would have to, or deceleration the object would have to experience in order to come to rest. Okay, so we still know that the initial velocity is equal to square root 10. That's what its speed was when it got to B. Its displacement is still 1 meter. However, this time we want to know what its velocity, or we want its velocity final velocity to be 0, and we want to calculate the acceleration. So what is the acceleration? So let's use our same formula again. We want 0 final velocity. Square root 10 squared will be 10. We have 2 times 1a, and so you can see we need an acceleration of minus 5 meters per second squared in order for this object to come to rest. Okay, let's go. Force equals mass times acceleration, Newton's second law again, this being the net force. Right? The weight component of the object is still going to remain unchanged, right? And the normal contact force is going to remain unchanged. The only difference now is going to be the coefficient of friction. So we're just going to put everything backwards into our equation and solve for the coefficient of friction. Okay? So to calculate the net force, right, we need to take the forces acting down the hill, and the force acting down the hill is this 1 Newton here. That has remained unchanged. So we have 1 Newton acting down the hill, right? The force acting against motion is the friction force, which is going to be minus mu, and we need the normal contact force. This has remained unchanged, okay? We calculated it over here, 2 cos 30. 2 cos 30 degrees, and this must be equal to the object's mass, which is unchanged at 0.2, and we calculated the acceleration as minus 5. And so you can see mu is our only unknown, and so with a bit of calculator work we can quickly, well, they want us to just show what the value is, and so, well, more importantly, they want us to give the exact value, right? So the exact value meaning we're going to leave our square root 2 in. So let's just change this. This is going to be 1 Newton minus the coefficient of friction, right? 2, right? Cos 30 is square root 3 on 2 equal to, right? Minus 5 times 0.2 is going to give us minus 1. if we swap these around, if I move the -1 to that side and I move this to this side, I'm going to get 2 equal to mu square root 3, because these 2's cancel out. And finally, solving for mu, we're going to get square root 3 on, oh, sorry, not that. We're going to get 2 on square root 3. We can go one step further if we want. We don't have to, but we can also rationalize the denominator if we want. So to do that, what we would do is multiply by square root 3 on square root 3. And this would give us 2 square root 3 on 3. So both answers perfectly acceptable.